The bit of mathematics that I want to talk about starts, as all bits of mathematics should really, with a problem. And the problem has been with me ever since I was an undergraduate studying biology in the years immediately after the war. At that time, we were fascinated by the work of the ethologists Konrad Lorenz and Nico Tinbergen. And one thing that Lorenz wrote about was the way that animals behave when they fight. And he pointed out that very often they don't use their teeth or claws or whatever it may be to the full extent, but behave in a very conventional way, as if they were being careful always to hit above the belt and so on, and may even surrender in a very conventional way. Now, I don't doubt the facts. In fact, I shall give some examples of conventional fighting behavior later. What I doubted at that time, and still doubt, was the explanation that Lorenz gave for this behavior. What in effect he said was that animals behave conventionally instead of really fighting in an escalated way, because if they did use their teeth and claws, animals would get hurt, and that would be bad for the survival of the species. Now, even then, I knew that evolution doesn't actually work like that. You see, suppose there were two kinds of animal in the population, one of which did indeed bite, scratch, kick, hit below the belt and so on, the other one of which was very gentlemanly and only did very innocuous things. Who would win? Well, obviously the first kind, the kind that fought in an escalated way. Who would pass their genes on to the next generation? Well, again, obviously the first kind. And even if it was bad for the species, so what? So I knew there was a problem there, but I was busy with other things, like getting a degree and so on. And I didn't seriously think about this problem for another 20 years, when I found myself having a holiday in Chicago. And Chicago is an odious place. There's really nothing to do except work there. And I decided that I would think about this problem. And I decided to teach myself some game theory. All I knew about game theory was that it was a bit of mathematics that had been invented by the mathematician von Neumann for studying human conflicts, business conflicts in particular, economic conflicts. And it seemed to me it might possibly be useful for studying animal ones. So I learned a bit of game theory, not very much. I didn't need to learn very much, as a matter of fact. And I invented a game which seemed to me to illustrate the problem of conventional fighting. I imagined that there were just two things an animal could do in the course of a fight. One was indeed to fight in an escalated way, and the other one was to display. And I supposed that there were really only two kinds of animals, which I called hawks and doves. You must remember this was being invented in America during the Vietnam War. And hawks fight in an escalated way until either they win or until you're seriously injured and forced to retreat. A dove, on the other hand, displays red breast or white wing bars or what have you. But if the other guy escalates, a dove runs away very quickly before he's hurt. And I invented this game, and I want to show you what's called a payoff matrix for this game, which is in the first diagram. And I want you to suppose that the value of the resource they're fighting over, which might be a territory or a female or an item of food or what have you, is V. The cost of being seriously injured is minus C. The units that this is being measured in will become clear in a moment. And here is a payoff matrix for the hawk-dove game. I always picture these myself as the guy on the left in one of these matrices. I can be a hawk or a dove, and you can be a hawk or a dove. And the entries in here are what I get if I'm, let's say, a hawk and you're a dove, in which case I escalate, you run away, I get the resource, I don't get hurt, I get V. If I'm a dove and you're a hawk, I run away quickly before I'm hurt, I don't get the resource, I get nothing. If we're both hawks, then we fight, one of us gets injured, one of us gets the resource. It sort of evens which I am, so I'll get V half the time and C half the time. On average, I can expect to get V over 2 minus C over 2. Finally, suppose we both display at one another. Well, for the moment, I want you to suppose that we can agree to just share the resource and have half each. So that's what's called a payoff matrix for the hawk-dove game. But because arithmetic is easier than algebra, let's put V equal to 2 and C equal to 4. The qualitative conclusions I'm going to draw don't depend on those absolute numbers, but they do depend upon C being bigger than V. And the payoff matrix now converts into that. Well, that's a payoff matrix. What are we going to do with it? I want you to imagine a population of animals playing this game. And each animal has a strategy. He's either a hawk always, or he's a dove always, Or maybe he plays sometimes hawk and sometimes dove. I want you to imagine they pair off at random, they play the game, and they start, before they've played anything, with some money in their pocket, if you like. Some sort of initial value. And every time they play a game, they change the money in their pocket by that payoff that comes into the payoff matrix, +1 or -1 or whatever it may be. After they've played a few games, they stop and they reproduce. This is a model of evolution, you must understand. So when they reproduce their kind, and hawks produce hawks, doves produce doves, and guys who sometimes do one and sometimes do the other, so-called mixed strategists, will produce mixed strategists with the same probability of hawk as themselves. But the number of offspring they will produce is going to equal the amount of money they've got in their pockets. So what these payoffs represent are the changes in what biologists call fitness, that's simply expected number of offspring, resulting from the fights. They then die, and their children proceed to go through the same thing again. And we imagine this population evolving. And we can ask, to what state will that population evolve? Well, it will evolve to something which is in this diagram called an ESS. That's short for evolutionarily stable strategy. Now, in words, an ESS is simply a strategy such that if all the members of the population are adopting it, no mutant strategy different from the ESS can come along and do better. And it's fairly easy to discover what properties an ESS must have. And the actual formalities of an ESS are shown in the second diagram. First of all, some notation. The phrase E, A, comma, B simply means the payoff to me if I play A and you play B. And I is some strategy which we're going to find out whether I is an ESS or not. And M is a mutant strategy. M has a very low frequency, P much less than 1, and I has frequency 1 minus P. And we can work right down here the expected fitnesses, i.e. amount of money in the pocket, of an I individual and an M individual in such a population. They start off with C in their pockets, and to look at an I individual, with probability 1 minus P, he meets another I and gets this. With probability P, he meets an M and gets that, and so similarly for M. Now, if I is an ESS, it must be true that this value is bigger than that. Wi is bigger than Wm for any M which is not the same as I. Now, looking at these equations, the C's are equal, they cancel out. If this term is bigger than that one, we can forget about these terms because they're small. So if this is true, it's an ESS. But maybe those two are equal, in which case it's an ESS if this is bigger than that. And that gives these conditions here, which are the so-called standard conditions for an ESS. Now, if we go back for a moment and look at the hawk-dove game, and we can see how this works out. We can say, well, all right, what's the ESS of the hawk-dove game? Well, it obviously isn't hawk, oddly enough. If we were all playing hawk, we would be averaging -1 per contest. A dove who came along, he'd get nothing, which is bigger than -1. So dove mutants can invade a hawk population. But dove isn't an ESS either. If we were all playing dove, we'd get 1. A hawk mutant who came in would get 2. So hawks can invade a dove population, dove can invade a hawk population, and it turns out that the only ESS is to play sometimes hawk and sometimes dove. For those exact values, these values of V and C, it turns out that the ESS is to play them 50-50, but if those numbers were a bit different, then it would be some other probability. Okay, so the first conclusion from a very simple model of this kind is that we may expect, sometimes at least, to find in nature what are called mixed ESSs, mixed strategies. Are there any real mixed strategies? Well, I'm only going to give you one example. It's a very familiar phenomenon that you all know about, but none of you have ever thought of it as being a mixed ESS. And it's this: there are the same number of little boys and little girls in the world born. Why? Well, those of you who know some biology will say, oh, well, it's to do with the way the X and Y chromosomes behave. But of course, that's, in a sense, nonsense. If natural selection had preferred there to be, if you like, 3 boys to every girl or 3 girls to every boy, there's no question that that could have been produced. So why, in fact, has the ratio that's been favored by natural selection, why is it 1 to 1? Well, imagine a world, if you will, in which women, let's say, can choose the sex of their children. For each child, they can choose whether to have a boy or a girl. And because we're talking about evolution by natural selection, what they must do is to choose that sex of child which will maximize the number of grandchildren they have. Which sex should they choose? Well, obviously, if most of the other women are having little girls, they ought to have boys. And if most of the other women are having boys, they ought to have girls. This follows quite necessarily from the fact that everybody has one father and one mother. So whichever is the rarer sex has, on average, more children. So you should always produce the rarer sex. But the only ESS, the only evolutionarily stable state, is when the two sexes are equally common, and then they both pay equally well. So there are mixed ESSs in the world, and the most obvious one is the one-to-one sex ratio. However, there's one thing about the hawk-dove game that I a bit slurred over. I knew I was doing it, mind you, and I hope you spotted me. And that was that bottom right-hand corner when I said, well, two doves can sort of have half each. But supposing it's something they can't saw in half, I mean, supposing it's a female or a, well, anyway, something you can't saw in half. All they can do is to display. This leads to a game which I've called the war of attrition game. All that the animal can do is to just go on displaying. And whichever one goes on displaying for longest wins. Now clearly, if displaying didn't cost anything and the resource was valuable, there's no solution to this game. They'd go on displaying forever in order to get it. So we have to suppose that displaying costs something. And the longer you display, the more money you pay. A human analogue of this game would be that we all start off with $10 in our pocket. No, sorry, let's not say we start off with $10. Let's start off with nothing. But somebody says, I'm going to give you a prize for winning this game you're going to play. And they hold out a $10 bill. And say, if you can win this game, you get a $10 bill. All you have to do is to write down on a piece of paper what you're prepared to pay for the $10 bill. That represents how long you're willing to go on for. So if you and I are having a contest, we each write down on a piece of paper, without showing the other one, what we'll pay for the $10 bill. Then, when we've both written our thing, we show it to the other one, and whoever's written the larger sum gets a $10 bill. But we both pay to the bank, not what we've written on our piece of paper, but the smaller sum. So if I write 6 and you write 5, I get the $10 bill, but we both pay to the bank 5. Both of us have to pay to the bank 5, because that's how long we had to go on, both of us, before ultimately I won. Supposing a population of people play this game, what's the ESS? What's the evolutionarily stable sum of money to write on a piece of paper? Well, it's at once obvious it can't be a fixed number. It can't be a pure strategist. Because supposing we were all writing $6, it seems a reasonable sum of money to give for $10 when you don't know you're going to get it. What would be average? Well, let's look at the actual formalities of the war of attrition game. Here it is. There are two players, A and B. It's me and you. I play A, you play B. If I play more than you, I get the reward and pay to the bank minus B, and you pay minus B. If you pay more than me, you get the reward, and we both pay A. If we both write the same thing, well, we sort of toss for it and take half each. But we both pay the B to the bank. Now, as I say, it clearly can't be a pure strategy, because if we all were writing down 6, we would get what? Well, we would get V half the time, which is $5 a game, half the $10, and we'd pay out 6. So we'd lose $1 a game, roughly. A mutant who came down and wrote $7 on his piece of paper would win all the contests and get $10 every time he played a game and only pay out 6. So he'd be doing better than we would. So he could invade. So sooner or later the population would consist of guys writing down $7. And then, of course, $8 could invade, and then $9. But at this stage, of course, $0 could invade as well. So there's no ESS for this game that is a pure strategy. So there has to be some kind of probability distribution that you sort of look up in a book of tables what to play this time with a probability. And it can be shown that the stable distribution is P of x is given by that expression there, 1 over v, e to the minus x over v. Now, just to indicate to you how you go about proving that. I'm not going to do the algebra because I'm jolly bad at algebra, but I'll give you a rough idea how you go about it. We know there's some probability distribution, P of x, which ought to be an ESS. So let I be that distribution, and let M be some pure strategy. then we can show that the expectation that M has, the pure strategist has against I, is given by that expression here. These are the cases when between 0 and M, if I lies between 0 and M, the pure strategist wins and gets the V. If I is greater than M, lies between M and infinity, he doesn't get the V. And that integral there, or the sum of those two integrals, tells you on average the expectation that M gets. Now, how do we find what P of X has to be if P of X is to be an ESS? Well, what we have to do is to find P of X such that this expression here is a constant. In other words, no matter what pure strategy you play, you get the same payoff. In just the same way as in the sex ratio game, whether you have a boy or a girl, you get the same payoff at the ESS, which is 50-50. Another way of putting that is that if I differentiate that expression with respect to M, it equals 0. And I'm telling you that the solution of that is the P of X that I gave you on the last sheet, and you can amuse yourself trying to prove it. I'm rather bad at fiddling with symbols, and it took me a good week to find that. Remember, the solution actually is a negative exponential. And there it is. I ought to have known at once that it was a negative exponential without doing any algebra, and I hope you can see why. You see, imagine that you and I are playing this game. We're sitting there staring at one another, waiting for the other guy to go away. Supposing we've been sitting there for 2 hours. We're actually in the same position then as we were right at the beginning. You're still there, I'm still there, the reward is still there. The reward hasn't changed. The cost of staying hasn't changed. We're in exactly the position we were at the beginning. There's only one probability function which has the property that its behavior now is the same as it was 2 hours ago. Because clearly, if I'm in the same position now as I was 2 hours ago, I ought to do the same thing now as I did 2 hours ago. The only function that has that property is a negative exponential. The probability of leaving per unit time is constant. Just the same way you get a negative exponential for radioactive decay. The probability of decay for the next unit time is the same now as it was 2 hours ago. So I didn't really have to do the algebra. I ought to have known it was that right away. Well, are there animals in the real world that play the war of attrition game? Well, there is one animal that does this. This is the male dung fly. This is a heroic piece of work by my friend Jeff Parker, who studied dung flies. This means lying on your face staring at a cowpat for hours. The females come to cowpats. When they get to the cowpat, they mate with a male who's already there, and they lay their eggs in the cowpat. Problem, supposing you're a male, how long should you stay at a cowpat? You see, the longer you've been with a cowpat, the staler and drier and sort of more boring this cowpat is, and the fewer females are arriving. So you ought to leave. But of course, if you're the only guy there, any female that does arrive, you're going to get. Whereas if it's a fresh cowpat and there's thousands of males around, then even if a female does arrive, the chances are that you won't actually be the lucky one to mate with her. So what you should do depends on what other guys are doing. If other guys are constantly dashing off looking for fresh cowpats, perhaps you should stay with stale ones. But if other guys are hanging around with the stale ones, you ought to go and look for a fresh one. And it turns out that the actual mathematics of it is exactly the mathematics of the war of attrition, of how long should you stay. And furthermore, male dung flies know that. And they do, in fact, stay a negative exponential length of time. And what's more, they've got the constant right, because there is a constant in that exponential. Otherwise, it could just be an accident. But they have actually calculated the constant right, and they do stay just the length of time that the theory says they ought. Now, okay, but there's something a bit ridiculous about this. If you and I were playing the war of attrition game, surely we would have the sense to say, well, let's not sit here. Let's not just sit here for hours staring at one another. Let's toss for it. And if it's heads, I'll take the reward and you go push off. And if it's tails, you have the reward and I'll push off. We wouldn't have to hang around for hours. We'd still have an even chance of getting the reward. And on average, we'd do a lot better. And I thought of that fairly early on. And then I thought, well, animals can't toss. I mean, there's no way they can toss coins. But it turns out that my insight was right, and that there's something equivalent to tossing coins that animals can do and do, but that I think I'll talk about in the second half of this talk. I finished the first half of this talk by saying that there's something a bit ridiculous about the war of attrition game, because surely human beings playing that game would simply toss to decide who wins. I can make that even more vivid by pointing out that if you calculate for the war of attrition game, what on average do you expect to win over a long series of games, the answer is nothing. You pay out to the bank almost exactly what you get from the bank. So you get nothing for it. The thing is ridiculous. Whereas clearly, if right at the beginning of the game we tossed for it, we would get V half the time, so we would get V over 2. So is there anything in animal behavior that can be like tossing? Now, what does tossing do? Logically, all that tossing does is to introduce an asymmetry into what was previously a symmetric situation. Now, there is one obvious asymmetry in many animal fights, and that is who got there first, or if you like, who is the owner. And it occurred to me that quite possibly mere ownership might help to settle contests. Now, I want you to go back to the hawk-dove game and imagine that ownership doesn't actually make you more likely to win an escalated fight. Ownership doesn't influence, doesn't affect the value of the resource, but it's there. You got there first, you're the owner in some sense, and the other guy is the intruder. And that means that your choice of whether to play hawk or dove can be made conditional upon whether you are or are not the owner. And so we can introduce a new strategy. And that gives us a payoff matrix that I put down here. This is exactly the same hawk-dove game as I played before. These top corner entries are just what we had before. But now we've got a third strategy, B, which for obvious reasons is short for bourgeois. What bourgeois does is to play hawk when he's owner and dove when he's intruder. And we can ask, what's the payoff to bourgeois? Well, if I meet a hawk, when I'm owner, I play hawk 2 and I get -1. If I'm non-owner, I play dove and I get 0. If I'm owner half the time, then I get the average of those two, which is -1/2. And similarly around the table. Here I get the average of those two, which is 1.5. Here you get the average of these two, which is 1/2. Here you get the average of those two. This is the interesting entry. Suppose we both play the bourgeois strategy. Well, either I'm owner and play hawk, and you play dove, in which case I get +2, or I'm intruder and play dove and you play hawk and I get nothing. So on average I got the average of 2 and 0, which is 1. And we can now see that bourgeois is, as a matter of fact, an ESS of this matrix, because if we all play bourgeois we average 1 per contest. A hawk mutant against us will get 1/2, can't invade. A dove mutant will get 1/2, and any mixture of hawk and dove will get 1/2. So B is an ESS, and it's fairly easy to show, as a matter of fact, that it's the only ESS. Now, what this seems to say is that animals ought to treat prior arrival or ownership of a resource as a conventional cue which settles the contest. Now, when I first thought of this, I thought it had to be ridiculous. I thought I'd been over-influenced by capitalist economics or something. But as a matter of fact, it turns out that it's often the case. Let me give you one example. It comes from the work of Hans Kummer on the Hamadryas baboon. Now, in the Hamadryas baboon, a single male will form a fairly long-term consortship relationship with 2, 3, 4 females. The females follow him around everywhere. He's about 3 times as big as they are, and he bites them fairly viciously if they try to stray. It's a fairly male chauvinist setup. What Kummer did was to discover how ownership is respected in consortships of this kind. And the next diagram shows his experiment, which is really very simple-minded. What he did was to take 3 baboons, 2 males called A and B, and a female called X, who have the property they don't know one another. They've never met one another before. Male B is put in a large enclosure with the female. Male A is in a cage in one corner. He can see out of the cage, but he can't get out. After about 20 minutes, male B will have formed a consortship with the female, who is now following him around safely. You then let male out of the cage. What happened when Kummer did this was that male A did not challenge male B for possession of the female. He skulked around, he avoided eye contact, and no fight took place. Now, if you think about it, that can mean one of 2 things. Either baboons have read my paper on the bourgeois strategy and know that they ought to respect ownership, that it is evolutionarily stable to do so. The other explanation, unfortunately, is that male A can see that male B has got sharper teeth or is bigger than he is, and that it would be rash to challenge him. But Kummer was able to rule out that possibility by repeating the experiment a week later with the same 2 males, but with their roles reversed, male B is now in the cage, and of course a new female. Now male A forms a consortship, and when you let B out, he doesn't challenge A for ownership. So it isn't that there's a difference between these baboons in size, it is that they do indeed respect ownership as a key to how the contest should go. And it turns out that most pairwise contests are in fact settled in this kind of way by an asymmetry which may be of ownership between the two contestants. The bourgeois strategy has been found in animals as distinct as baboons and butterflies, and it's been found in great tits, it's been found in bees, it's been found all over the place. But of course, the asymmetry need not be of ownership. It may be of actual size, provided that the size can be perceived by the animals. Clearly, a size difference can't influence their behavior unless they're aware of it. Influence who wins the fight maybe, but it won't influence whether there is a fight. A friend of mine, Susan Reichert, has been working on a funnel web spider in the deserts of America for many years now, and they fight over the possession of webs, which are hard to come by if you live in the desert area. It's not so much the web is hard to come by, but a suitable place to build a web is hard to come by. And they fight quite viciously over these webs. However, if there's a substantial difference in mass between the two spiders, that difference settles the contest in favor of whoever is heavier, whether the heavier spider is the owner or an intruder. You may say, how do we know that it's mass? Well, Susan has a very simple and elegant experiment to demonstrate that it's mass. What you do is you catch two spiders and you choose two that are indeed the same weight. You let one of them occupy a web, he said the owner, and you allow the other one to challenge. But before you do this, you glue onto the small piece of lead shot onto the back of the intruder, who is now heavier. And as soon as he gets onto the web, the other one runs away. Of course, a web is a great way of measuring mass. You see, if you get a web is a sort of elastic thing. If you get on the web and you're a big spider and you go like this, the other small spider will be going like this. It's a very easy mass estimator. And indeed, we can show by putting the bits of shot on that the smaller spider retreats at once. So asymmetry is not only of ownership, but asymmetry is of size, and other kinds of asymmetry can settle contests in that kind of way. So it seems that the bourgeois strategy works all right. The next topic to which evolutionary game theory has been applied has been looking for the evolution of cooperation, and particularly cooperation in what's called the prisoner's dilemma game. Now, the prisoner's dilemma game is a famous game in the history of game theory, and it's shown on the left of this diagram. The idea is that it's a contest between two people, or an interaction between two people or two animals, in which they've got a choice of strategies, C and D. C stands for cooperate, and D stands for defect. And I've put in the payoffs here. And the idea is that, these are my payoffs, remember. Supposing you cooperate, I get 5 if I defect, and only 4 if I cooperate. So I say, if he cooperates, it pays me to defect. Suppose you defect. I get 2 if I defect, and 1 if I cooperate. So again, it pays me to defect. So no matter what you do, I'm going to defect. And of course, the rules are just the same for you. The payoffs are just the same for you. So no matter what I do, it pays you to defect. So we both defect. Okay, so we both defect, and we both get a payoff of 2. But this is ridiculous, because if we both cooperated, we would have got a payoff of 4. This is the central paradox of cooperation. That it's often the case that cooperation would pay everybody, but if you look at it from your own individual selfish point of view, it looks as if it'll pay you to defect. Question, can animals solve this problem, let alone human beings who don't seem to be very good at it? Well, if there's only one game, then the only ESS of this matrix is to defect. This is the ESS. But suppose you play the prisoner's dilemma game repeatedly against the same opponent. Then, of course, you can make what you do in one game conditional on what happened in the game before. And in particular, you can play a strategy which I've called TFT here, which is short for tit for tat. What you can do is to say, the strategy tit for tat goes as follows. In the first game, I will cooperate. In all subsequent games, I will do what you did last time. So if you cooperated last time, I'll cooperate. If you defected last time, I'll defect. And what I've written down here is the payoffs for two strategies: defect, always defect, regardless, and tit for tat, in a run of 10 games. Just to see how this goes. Supposing I'm a defector and you play tit for tat. Well, in the first game I defect and you cooperate, so I get 5. But from then on, you defect, because I defected last time, and I get 2, because we're both defecting. So I get 2 9 times, which is 18, plus 5, which is 23, so it does seem to add up right. And if you work it through, you'll find those are actually the right payoffs. Now you'll see that tit for tat is in fact an ESS, because if we all play tit for tat, we all get 40, and a defector will only get 23, so it's a lot better. The defect cannot invade a population of tit for tatters. But oddly enough, defect is also an ESS. There's no rule which says there's only one ESS of a game. This game has 2. If we all defect, we all get 20, and tit for tat can't invade because it only gets 19. It's only got to be done a little better than that to invade. So when we do, as we often do actually, find cooperation between animals, and cooperation is not at all uncommon between members of a species, we tend to think of it in terms of this game, but we have the problem of how did it get going. Clear enough that once it's established, it's uninvadable, but how did it get going? And we tend to go in for an argument which is really rather away from the topic of my lecture, that cooperation starts between animals who are relatives, who share genes, and this brings us into a whole new ballpark of how should animals behave when they share a number of genes in common. But we think that that kind of process gets you out of this corner, but once you're in this corner, you should go on cooperating with anybody, whether they're relatives or not. So game theory does make some kind of sense of the evolution of cooperation between animals. The last thing I want to talk about is whether games necessarily have ESSs. I mean, can we invent games that don't have an ESS? Well, as a matter of fact, we can do pretty easily. I've put on the next diagram a kind of summary of what we know about the existence of ESSs. First of all, for what I call two pure strategy games, that's a game like the hawk-dove game or the cooperate-defect game, where there are only two pure strategies, and all you can do is either to play one of those or to play a mixed strategy between them. Given that, we can show the following two things. First of all, that there is at least one ESS. There may be two. I've shown you a game which has two, but there must be at least one, maybe pure, maybe mixed. The second point is this, that if there is a mixed ESS, let's say it's 50-50 hawk and dove, play hawk half the time, play dove half the time, we can then ask, well, supposing individuals couldn't play mixed strategies, supposing the best an individual can do is to play either hawk or dove, then, of course, a population consisting of half hawks and half doves would in some ways be rather like the ESS population. And we can show that if the mixed ESS exists, then the corresponding what we call polymorphism, that is the case where everybody's a pure strategist, but some of them are hawks and some of them are doves, but with the same relative frequencies as in the ESS, we can show that this is stable too. Unfortunately, because, you know, God is never always just to us, in the three pure strategy game, these things are not true. First, there may not be an ESS at all, and secondly, even if there is an ESS given by some vector of probabilities, then the corresponding mixture of pure strategies may not be stable, and indeed vice versa. So we're in bad shape. Things get complicated when there are three pure strategies. And just to give you some idea of how complicated the simplest of games can be, I want to discuss a game which I discover is actually universal. I last saw it being played by 3 little children in the streets of Singapore, but I bet you've played it, and it's the game rock, scissors, paper. Rock, scissors, paper. I hope you all know the game, but as I say, it does appear to be one of those rather jolly human universals. It turns out that rock, scissors, paper as a game does not have an ESS. I've written a payoff matrix for rock, scissors, paper. Here it is. If I play rock and you play scissors, I blunt your scissors so I get 1, but if you're paper, you wrap my paper and I get -1, I lose. And similarly for the rest. We have to decide what's going to happen if we both play the same, and I've supposed here there is some small cost, E, that's a small positive number, there's a small cost to a draw. We've wasted time. Okay. Now, you can play with this on a computer. It's really rather a nice game to simulate on the computer. You can get some very jolly dynamics out of it. It's possible to show that the mixed strategy, play rock with probability of 1/3, scissors 1/3, paper 1/3. You toss a three-sided dice of some kind to decide what to do in each game. That's an ESS. If everybody's doing that, it cannot be invaded by any other strategy. But oddly enough, if you're only allowed to do pure strategies, you've got to be a pure rock guy or a pure scissors guy or a pure paper guy, the corresponding polymorphism, let's say 1/3 rock players, 1/3 scissors players, 1/3 paper players, is not stable. And you get the following dynamics, which I've shown here, that even if you start fairly near the middle of the triangle, you oscillate out like this in ever-increasing circles until you finish up going almost round the edge of the space. So here we have a game which has an ESS, but the corresponding polymorphism isn't stable. If, on the other hand, we make epsilon negative, that's to say, instead of there being a small cost to a draw, there's a small reward for a draw, there isn't an ESS of any kind. Not even this 1/3, 1/3, 1/3 is an ESS. Those things are not all that difficult to prove analytically, but you can have a lot of fun playing this game on the computer, and in particular you can ask, well, given that there is an ESS, what happens? And supposing we have a mixture of pure strategists and mixed strategists and so on, can we predict the dynamics? And I think if you do put that onto a micro, you'll really be rather surprised by the complex dynamics you can get out of it. I think it'll be fairly obvious to you that the models, the hawk-dove game, the war of attrition game, the bourgeois strategy game, and so on, are a great deal simpler than anything that actually happens in the real world. But they do illustrate, I believe, that even very simple models, once you understand them, once you've got the logic of them, can actually be quite illuminating when you look at real animals.